All right, I have the textbook open. Let me go to chapter 7. What's chapter 7? Oh, properties of expectation. Let's see. Let's go to problems. All right, 37. Let me scroll up. What was the exact questions? 37 and 53. Okay. So here is 37. Let me paste it. So that's 37 over there. Is that big enough for you guys to see? And then let me take 53 as well. Okay, 53 I'll put over here on the side for now. All right, so let's take a look at these two questions. All right. 37 says a die is rolled twice. Let x equals the sum of the outcomes and y equals the first outcome minus the second. Okay, sure. So they want us to compute the covariance of x and y, which means we should probably get the distribution for x and y first. Let's go ahead and do that. So let me make a table. So let's do x first. Let's make that thicker. So what are possible values of x? X is the sum of the outcomes. So if that's the case, then the possible values of x are from 2 all the way to 12, right? So x can be from 2 to 3 to 4 to 5 to 6, 7, 8, 9, 10, 11, and 12. You'll also need the probabilities. So what is the probability of getting a sum of 2 from 2 dice? The only way to get that is to get a 1 and a 1. So that's 1 out of 36. And then the only way to get a 12 is to roll a double 6, which is also 1 out of 36. Okay. And then the rest of them, you'll have to sort of think it through. Like, you know, the rest are not 1 out of 36 because there's different order you can do it in. Anyways, I don't want to go into too much of the details of this problem, especially not the calculations, but I just want to like show the setup because calculating the covariance just follows a formula once you have everything set up. So I guess we can fill in some of these. So how would you get an 11? To get an 11, you would need to roll a 5 and a 6 or a 6 and a 5. So that'd be 2 out of 36. So is everyone okay with how you would go about filling out this chart? If so, let's move on to y, the other variable. And then p of y. So y is the first outcome minus the second. That's not a common way to deal with the two outcomes, but I guess we can think about it. What are the possible values for y then? So if you get a 1 minus a 6, that's a -5. You can get -4, -3, -2, -1, or you can get two of the same values, 1, 2, 3, 4, 5. Okay, so you would fill out this chart too for the probabilities. So for example, let's think about how you can get a difference of 0. That means that you you roll 2 of the same numbers on the 2 dice. So I think there's 6 different ways to do that. So 6 out of 36. This one, I believe, is also 1 out of 36, because this has to be, you roll a 1 and a 6. So yeah, you would fill this chart in. Now, assuming you have both of these charts filled in, what was the formula for covariance? I need to pull that up from, what was it?
I think it's the sum of x of I minus the mean of x times y of I minus the mean of y over either n or n minus 1, depending on whether it's the sample or the population.
Yeah. I think that one is the covariance formula for data sets, though.
Oh, okay, never mind.
There's a separate covariance formula for random variables as well. Let me pull up, but yeah, you're probably right. But let me pull up chapter 7 just because I don't remember it. Let's see, properties of expectation, covariance and correlation. Okay, so it was the following: expected value of x times y minus e of x times e of y. So let me write that down. Covariance of x comma y equals expected value of x times y minus e of x times e of y. Oh, that honestly does not look that easy to do. Well, the second part is fine. E of x and e of y, you should be able to calculate those no problem, given you have these 2 tables filled out. But e of x times y, that might be a little difficult, because first of all, you would have to make a separate table. You would make the variable x times y, and let's see. Yeah, there's a lot of values for x times y. So for example, the one value you can get is -10, right? When you do 2 times -5, that would give you -10. And then figuring out the probability for that is also requires a lot of thought. So for example, what is the probability that you get a sum of 2 and a difference of -5? You know, that's what I have to think about. So that would be how you would fill out this table. Let's see if we can actually fill out at least one of these entries. So let's consider.
I don't think that would be possible to get a sum of 2. Sorry, a difference of -5 and then a sum of 2.
Yeah. I just thought about that. That doesn't seem like it'll be possible either. So the probability would be 0 then for that one. But is there one that doesn't have a probability of 0? Let's see.
Well, like a sum of 2 and then a difference of 0 would just be 1 and 1.
Right. So you're doing this one here,
and then y 0.
This one here. So then that would be 0. Which one? So that's 1 out of 36. Yeah. Okay. So these entries are you have to go through all the possible combinations, but that would be the main idea. I'm not sure why this question asks you to calculate covariance, but seems pretty complicated. But anyways, once you have this table filled out, you would calculate the covariance. So the expected value, like we all know, is just the summation of like this number times this number plus this number times this number, and so on and so on. So that would be the process. I'm not going to go through all of it because that would take forever, but that's the main idea. Okay, so oh, someone just sent me a DM. Oh, it was okay. Scratch 53. I forget which problem I saw, but 53. That's like exam we did in class. Okay, sure. We can skip 53. But I mean, since I already have it here, is anyone curious to see 53, or are you guys all okay with 53 as well?
Yeah, you cover this one in class.
Okay. All right. In that case, let me pull up chapter 9. Sure. Okay, so here's chapter 9. This is titled Additional Topics of Probability. So everything that we're about to go through is what I would consider not or non-essential. Sorry, um, non-essential to probability theory, but it's good to know, especially if you plan on taking further courses like Stat 312. So what are some additional topics that we will cover? Well, it's mainly two things. So there's the first thing, which is called Poisson processes. And the second thing is called Markov chains. So those are the main two topics that we will include in this chapter. And yeah, so let's start with the first one. Before we start with Poisson processes, let's just familiarize ourselves or review the Poisson random variable. So this we already know. This was from the discrete random variables chapter. So the Poisson random variable has the following parameter, lambda, which is always positive, and lambda is referred to as the rate or the mean parameter. And the random variable has the following probability mass function. So it's lambda to the x, e to the negative lambda over x factorial, where x is 0, 1, 2, 3, so on and so on. Okay. The expected value as well as the variance are both equal to lambda, which is pretty convenient. And then, does anyone remember what the Poisson random variable is usually used to model? Like, what real life situations is this good for? Time or something. Well, not exactly time. In fact, time would not be a good would not be modeled by Poisson very well, because time is usually continuous, and Poisson random variables are not continuous. So what time is not one of them, but what was one of them? Does anyone remember? Probability for something to occur in a given amount of time. So like number of earthquakes in a season. Yeah. Something along those lines. I don't remember the exact description I gave, but it's used to model like the number of events. Events are that usually considered are things like catastrophes or number of accidents, so things like that. So those certain events are usually modeled well with Poisson random variables. Okay. Now let's go on to more detail on what a Poisson process is. So let's take a look at this slide here. So we're given a lambda, right? That's what we need for Poisson random variable. Let lambda be greater than 0, and it's fixed. So the counting process n of t, where t is some positive number or 0, is called the Poisson process with the following rate if the following conditions hold. So n of 0 equals 0, n of t has independent increments, and the number of arrivals in any interval of length has Poisson random variable lambda times t. So that probably didn't mean much, but let me explain what, like in general, what a Poisson process is used for. So anytime you're given a Poisson random variable, a question might specify the lambda for a specific time interval. So for example, a question might say, this is a Poisson random variable with lambda equals 5. If the time was like 1 hour or something, right? So in 1 hour, you get 5 accidents. However, what a question might do is they'll say, well, okay, what if you don't consider 1 hour? What if you consider 2 hours? Or what if you consider half an hour? How does that change your lambda? And according to bullet point number 3 here, it basically says that you have to just scale your lambda parameter by whatever interval you're given. So for example, if the original time was 1 hour and the question wants you to scale it to half an hour, then just divide lambda by 2, okay? And that will be your new parameter. So that's what the main idea of a Poisson process is. But let me also go through a little more detail, points 1 and 2. So point number 1 says n of 0 equals 0. So what does that mean? Well, that basically means that at the start of your time interval, no occurrences have happened yet. So for example, let's say you're thinking about like the beginning of the day. So when the day starts, you're going to assume that no accidents have occurred. That's what the first bullet point is assuming. And then point number 2 says NFT has independent increments. So what does that mean? Well, it basically means that if you were to say analyze 2 different time intervals, so let's say you're analyzing from 10 a.m. to 11 p.m. No, wait, 10 a.m. to 11 a.m. So let's say that's your first interval, 10 a.m. to 11 a.m. And then you also want to compare that to, say, what's going on at 1 p.m. to 2 p.m. So those 2 time intervals should be independent, okay, in order for it to qualify as a Poisson process. So those are the 3 assumptions that we're making here to see what qualifies as a Poisson process. All right, and then let's see, is there anything else I wanted to mention regarding this? I think that should be it. So let's take a look at an example of what a Poisson process question will look like. Okay, so I have an example here. Let's do it together. So this question is not analyzing accidents or tsunamis or catastrophes or things like that, but rather it's modeling the number of customers arriving at a grocery store, which is pretty interesting. Usually one of the more common things that's modeled with a Poisson process. So yeah, let's try this. The number of customers arriving at a grocery store can be modeled by a Poisson process with intensity lambda equals 10. Okay, so yeah, some questions might refer to the parameter as intensity as well, because it's like the more customers that arrive per hour, then the more intense it is. So they give us our parameter of 10, and then let's read what they want us to find. So find the probability there are 2 customers between 10 and 10:20. Okay, so how do we go about doing this? Let's use purple. So number 1, that's not purple. Okay, so number 1, the original parameter lambda equals 10. This is for per hour, right? So this is per hour. However, for question number 1, they do not want us to analyze for a whole hour. They want us to analyze from 10 to 10:20. So that's only 20 minutes. That's not a full hour. So what do we need to do here? Well, what we need to do is basically scale our parameter to account for this change in time. So instead of using lambda equals 10, we're going to use lambda equals something else. So we need to ask ourselves, 20 minutes is how much of an hour? It's basically a third of an hour. So we're just going to change our lambda to 10 times a third of an hour, which is 10 over 3. This is going to be our new lambda that we're going to use to answer this probability question. So yeah, that's basically it. We're finding the probability that there's 2 customers, so x equals 2. What was the Poisson PMF again? Let me see. Okay, lambda to the x. So 10 over 3 to the x, e to the negative 10 over 3 over x factorial. So our x is 2. So let me go ahead and replace that. Uh, 2 here, 2 here. Okay. And then use a calculator. Divided by 2. Okay. So I got 0.037 approximately. So this is the probability that 2 customers arrive between 10 and 10:20. Let me double check that. That seems a little bit low, but let's see. 10 divided by 3 squared times e to the negative 10 divided by 3 divided by 2. Oh, okay, I got something different this time. So what did I do the first time? I got 0.198 this time. I don't know if anybody of you want to check that for me, but yeah, the setup for this formula should be correct. 10 over 3 squared, this should be in parentheses, times e to the negative 10 over 3 over 2 factorial. So that's question number 1. Let's try question number 2. So find the probability that there are 3 customers between 10 and 10:20, and 7 customers between 10:20 and 11. Okay. So we have to think of this in 2 separate intervals. So between 10 and 10:20, for that interval, we already established that the lambda is 10 over 3. So 10 to 10:20, lambda is 10 over 3. Now let's analyze 10:20 to 11. So 10:20 to 11, that's 40 minutes, right? So that would be, the lambda here would be 10 times 2/3 of an hour, which is 20 over 3. So those are our respective parameters for each interval. And then we can do the following. So we can just calculate probability that x equals 3 for the first interval times the probability that x equals 7 for the second interval. And the reason why we're able to just multiply it through like this is because from the previous slide, we mentioned that intervals are independent. So we can just multiply it through. So this would be 10 over 3 to the 3rd power, e to the negative 10 over 3 over 3 factorial times our parameter is 20 over 3 here to the 7th power, e to negative 20 over 3 over 7 factorial. Okay, and then whatever this is your answer. I think I got 0.0325. I think that's right. Okay, so yeah, there you go. This is a good example of a Poisson process problem. So any questions for that?
This is just the Poisson distribution, but like with an extra rule, essentially.
Yeah, pretty much. Mhm.
Why is it called the Poisson process?
So one of the reasons why it's called the Poisson process is because this actually is one of the subtopics of stochastic processes, which is stat 312. And I decided to skip the definition for what a stochastic process is, but mainly because it's like a subtopic. That's why they call it a Poisson process.
All right, thanks.
Yeah, this is just a name for now. So, all right. Any other questions? Okay, so if there are no questions, then you guys should try this one. This is also a very similar question that will test your knowledge of Poisson random variables and the assumptions for the Poisson process. So yeah, try this. Did you guys end up shopping during the holidays? Couldn't find any deals you liked. Oh, well, that's a shame. You finished most of your shopping. Okay. For those of you who did go shopping, what did you buy? Clothes? Oh yeah. Me too. I ended up buying some clothes too. It was funny, like my original plan, like way before the holidays, was to buy things like dress shirts and suits because I was assuming that I would be working like in an office right now, like in a cubicle or something, because my office is like that. But because it's all work from home, I had to change plans and buy sweatpants instead. But yeah, clothes is a very common thing to buy. And if you bought any of you bought cooler things like I don't know, electronics or things like that? I guess no one. Tools rarely go on sale. Tools like a power drill? For automotive applications, like an air wrench? Like a breaker bar? Is that what you mean by tools? Yeah, Well, I don't know. I don't go to Home Depot that much, but like I think they do have sales, but I don't know. Yeah. I have 3 tools like in my possession. I have a Makita power drill and an impact driver, and then I have a like I forgot what's that saw thing called. I think it's like a reciprocating saw or something. But yeah, tools are, I guess they're fun as well. Hammer, duct tape, and zip ties. Yeah. I mean, I don't know, like if you're gonna repair stuff like that, it would be kind of. I mean, you could probably repair a lot of things, but it would just look really funny in the end. Okay, so are you guys able to get the answers for these questions? Yes? Okay, good. So in that case, let's go over them. The number of clients arriving at a branch of Chase Bank can be modeled with a Poisson process with lambda equals 12 customers per hour. Okay. Find an expression for the probability that over 20 customers arrive between 10 a.m. and 12 p.m. So how much time is that? That's 2 hours. Okay. So if it's 2 hours, then we have to scale our lambda to 12 times 2, which is 24. Okay. And then we want to find the probability that there's over 20, so x is greater than 20. So before we write the expression, over 20 customers means probability of 21 customers plus the probability of 22 customers, or maybe it's 23 customers. And Poisson doesn't have an upper limit, so this goes all the way to infinity. Okay.
Yeah, that question seems like it would be a lot of work because you'd have to find the inverse from 0 to 19, right? 0 to 20.
Yeah. I think that's why this question says just find an expression. So we can't really do it this way, but like you said, we can find the inverse. That would be 1 minus probability of 0 all the way up to probability of 20. So I think that's what this question means by expression. So that would be it. And then if you wanted to, you can, specify like probability of 0 is lambda to the 0 power e to the negative lambda over 0 factorial. But I think that's unnecessary. So that would be part A. Yeah, that should be fine. Part B says, find a probability that no one arrives between 1 and 1:30 and 2 and 2:20. Okay, so these are 2 separate intervals, which means we can assume they're independent, so we can calculate them both separately. So the first interval is 30 minutes long, which means we have to scale lambda to half of its original value. So this would be 6. And then the other one, 2 to 2:20, that's 20 minutes. So that's 1/3 of the original value. So here lambda would be 4. Okay. So then if we were to find the answer, no one arrives. So that's probability that x equals 0 for both intervals. So it's going to be lambda, it's 6. 6 to the 0 power e to the negative 6 over 0 factorial times 4 to the 0 power e to the negative 4 over 0 factorial. Okay, whatever that is. But this is the probability that no one arrives in both of these intervals. Okay, and then part C says to find the expected value and variance number of customers that arrive between 10 and 11:30. So this is 1.5 hours, which means we have to scale lambda by 1.5, which is 18. Okay, so lambda here is 18. We already assume that this is a Poisson process. So the number of customers that arrive between 10 and 11:30. Let me write it out as a sentence to make it explicit. Number of customers that arrive between 10 and 11:30 is Poisson with lambda equals 18. Okay, so that's how you can write it as a sentence. So if that's the case, what is the expected value in variance?
18.
Yes. So E of number of customers equals the variance of number of customers, which are both equal to 18, because that's the property for Poisson random variables. Okay, great. Yeah, that should be it. So any questions on Poisson processes? I understand this is pretty simple because it's kind of like just Poisson random variable with some assumptions. Yeah. Okay, let's move on to the next thing, which is actually still related to Poisson process. So back to the slide. Okay, so now we have this thing called inter-arrival times. So what is this? For Poisson processes, we were interested in the number of events that occur, right? So number of accidents, number of catastrophes, number of customers that arrive, number of whatever, right? So now let's shift our focus to something else. So let's read the slide. Suppose instead of modeling the number of arrivals, we are interested in the amount of time that passed between each arrival. So this is what we mean when we say inter-arrival times. It's the amount of time that passes between each customer or between each accident or whatever. So we have this little picture right here, this number line, I guess, or timeline. The blue line is T for time. And then on the bottom, we have T sub 1, T sub 2, T sub 3, T sub 4. Those are basically like, think of it as like each customer. So T sub 1 is the first customer, and then T sub 2 is the second customer, and then the third customer, fourth customer. And then if you were to consider the amount of time that passes between each customer, that's where the X variable comes in. So X sub 1, you refer to X sub 1 as the first inter-arrival time. So it's the time that passes between 0 and the first customer. And then likewise, X sub 2 is the second inter-arrival time, which is the time that passes between the first customer and the second customer, okay? So that's how we give notation to inter-arrival times. So what can we say about inter-arrival times? More specifically, does it follow some sort of distribution that we're familiar with? It turns out that it does. So this is the conclusion that is established from the textbook. Let's say NFT is a Poisson process with rate lambda. Then the inter-arrival times, X sub 1, X sub 2, and so on, are also independent. And their distribution actually follows an exponential random variable with lambda equals the same lambda from Poisson, okay? So that is the conclusion that the textbook came up with. And if you want to like see the full proof, it's on page 418. But yeah, let's think about whether or not this, seems reasonable from an intuitive standpoint. So, well, the first reason why it's intuitive is because if you were to think about the amount of time that passes between each customer, time is continuous, right? So it makes sense that whatever distribution it follows a continuous distribution, and exponential distribution is indeed continuous. So yeah, this does make sense. As for the reason why it's exponential, there's really no intuitive explanation for that, unless you want to read the proof, which, I'm not even sure if that would help a little bit, but yeah, that's the conclusion. So just to recap the difference, if you're talking about the number of customers, that's Poisson, but if you're interested in the amount of time between each customer, that's exponential, okay? So let's do an example. Screen. Okay, so here we have let n of t be a Poisson process with intensity lambda equals 2, and let x of 1, x of 2 be the corresponding interarrival times. Okay. Find the probability that the first arrival occurs after t equals 0.5. So, we're gonna have to think of it in terms of like hours, I guess. So t equals 0.5, think of it as like half an hour, but we can just use 0.5, it's fine. Okay, so let me draw a diagram. Part A, here we have our timeline. This is no one here, and then this is the first arrival. We'll label it as t sub 1. And then this interval here, the time that passes between 0 and t sub 1, is going to be labeled as x sub 1, which is the first interarrival time. Okay, so the question is asking us, what is the probability that the first arrival occurs after 0.5? So in other words, find the probability that x sub 1 is greater than 0.5. So this distance here, we want to know what's the probability that this distance is greater than 0.5. If we want to answer this question, we have to know what distribution x sub 1 follows. Now, because x sub 1 is an interarrival time, we can say that x sub 1 follows an exponential distribution. This is exponential with lambda equals 2. Okay, so does anyone remember the details for exponential distribution? What was the PDF?
The PDF was lambda e to the power of negative lambda times x.
Lambda e to negative lambda times, like that?
Yeah.
Yeah, I think that's right. This is the PDF. Okay. Cool. So we're interested in the probability that's greater than 0.5. So greater than is the right-hand side.
Wouldn't you use the CDF here?
Well, yeah. So the CDF will give us left-hand side. Let's recall the CDF too. So what was that? CDF.
1 minus e to the negative lambda times x.
E to negative lambda times x. Yeah, cool. This will probably come in handy as well. So CDF, if you guys recall, is the left-hand side of a certain position.
Okay, so we should be able to find the CDF, so 0.5, and then it's just the inverse of that.
Yeah. So this would just be 1 minus the probability that x is less than 0.5, which is 1 minus e to the negative 2 0.5. So this is, let's see. Okay, so I got approximately 0.37. Okay, cool. So that is the probability that the first arrival occurs after 30 minutes has passed, or t equals 0.5.
I got negative 0.37.
Negative 0.30. Well, probability shouldn't be
Yeah,
negative.
it shouldn't be negative. That's probably an issue on mine.
Let me see if we can like verify with algebra here. So 1 minus 1 is nothing. And then you distribute the negative, that's a positive e to the, yeah, it should be positive. It's positive.
Yeah, it's just an issue with my calculator then.
Oh, okay. All right, so 37% approximately. Let's try part B. So given that we had no arrivals before t equals 1, find a probability that x sub 1 is greater than 3. Okay, so let's unpack this sentence right here. So we are saying that, wait, let me draw the number line. So this is t, and then this is, let's label time 1 here. So this is time 1. And then let's say this is time 3 here. So we're saying that we want to find the probability that x of 1 is greater than 3. So it's x of 1, the distance of x of 1 is going to be greater than this distance here. So it's going to go like past the 3 mark. How do we write this in notation? So it's probability that x of 1 is greater than 3. But they also gave us a conditional statement. So they're saying that given we have no arrivals before t equals 1. So this is basically saying that it's given that x of 1 is also greater than 1, right? Because x of 1 is the time until the first arrival. So if there's no arrivals between t equals 1, then that means x of 1 is already greater than 1. So this is the sentence in math notation. Okay. All right, so where can we go from here? Do we want to apply the conditional probability formula? So we can, but there's actually something else we can do to avoid using the conditional probability formula. And what we can do stems from the fact that we're dealing with exponential distributions. So I don't know if you guys recall, but there was a special property for exponential distributions called the memory list property. Does that sound familiar to you guys? Does that ring a bell?
Yes.
Yeah. Do you guys remember what the memory list property stated?
If I recall correctly, it had something to do with if you have an exponential distribution, let's say you're finding like within an interval of 15, if you start at like a third of the way through, it would be as if you're finding the probability from like 0 to 10. Basically, you don't remember what the previous probability was.
No, yeah, that's exactly what it is. Very good. So over here, we already passed the time of 1, and we want to get from 1 to 3. So the memory list property states that instead of writing it this way, we can write it as probability that x1 is greater than 3 minus 1, or 2, basically. So instead of going from 1 to 3, it's equivalent to going from 0 to 2. So this is what we can rewrite it as using the memory list property. Okay. Yeah. So also don't confuse this with independence. I think someone asked me the question. I don't remember who it was, but what is the difference between memory list and independence? So memory list allows us to rewrite the two statements as such, like from here to here. However, if you were to apply independence, you wouldn't get this equivalence. You would actually just get equals probability that x1 is greater than 3, which is obviously not the same. But yeah, we're not using independence here. We're using memory list. So this is not what we can rewrite it as. Delete. Okay, so if this is what we're dealing with, then we should be able to find the answer. This would be 1 minus the probability that x of 1 is less than 2, which is 1 minus e to the negative 2 times 2, which I think I got 0.0183. Okay. All right. And then part C. So part C says, given that the third arrival occurred at times t equals 2, find the probability that the fourth arrival occurs after t equals 4. So let's write this in notation here. Find the probability that the fourth arrival occurs after t equals 4. So our number line, t equals 3 is here, and then t equals 4 is here. Wait, no, they wanted 2. T equals 2, t equals 4. So they want the third arrival and the fourth arrival to be between 2 and 4. Yeah, I mean, it's not really relevant that they're calling this a third and a fourth arrival. You can just think of it as like the 0th and first arrival. So this is basically the probability that x, technically it's x of 4 is greater than 2, but all the x's are the same. So this is the probability that x of 1 is greater than 2, which we already did for part B. So that's also 0.0183. Yeah, and I guess this also is using the property that all the interarrival times are independent, so you don't have to consider what happened beforehand. Like the probability of x of 4 is greater than 2 is the same as probability that x of 1 is greater than 2. So it's going to be 0.0183 again. Okay. And then part D says, I start watching the process at time t equals 10. And let t be the time of the first arrival that I see. In other words, t is the first arrival after t equals 10. So find the expected value of t and the variance of t. Okay. So what we established is that this is an exponential variable with lambda equals 2. So does anyone remember the expected value and variance formula for exponential stuff? So expected value of exponential.
I think it was 1 over lambda.
I think it's right. 1 over lambda. Was the variance is 1 over lambda squared? Is that right? I think that was. Okay. Cool. So if we know that, let's calculate these values for our question here. So our lambda is 2, which means e of x is 1/2, and then variance is 1 over 4. Okay. So then the answer to part D. So they're saying that they started watching the process at time 10, and then they want to consider what time will the next arrival be, basically. So if you're starting at time 10, the average time that will pass until the next arrival is, according to the expected value, is 1/2. So I guess you just add them together to get 10.5. E of t equals 10 plus 1/2, which is 10.5. So what does that mean? Like, how do I restate that as a sentence? It's basically saying that if you start watching the process at time 10, let's assume this is hours. So let's say you're starting at 10 hours. They're asking you to figure out what's the expected time until you see the next arrival, which is 10.5 hours. Okay, so that's how you would restate it as a sentence. And they also want the variance of the time. So the variance, remember, is a measure of spread. So you don't add that to that time. So the variance of t is going to be just 1/4. Okay. All right, so that should be it. Are you guys okay with inter-arrival times? But not just that. You have to be okay with how to tell whether a question is asking you to figure out to use the Poisson random variable or the exponential random variable. So make sure you do look out for that. So what do you guys think? Are you guys okay? Okay. In that case, I will give you guys one last question to try on your own. So try this. Who was it that asked about or mentioned about buying tools? Whoever it was, like, do you work on cars? Yeah. I almost got a car this year, but my plans got ruined because all the prices are out of control right now. So I decided to not buy a car this year. But yeah, cars are cool, I guess. I had a phase, I think it was like a couple months ago. I was watching Chris Fix like every single day. You got to go out of state. Yeah, but like, I don't want to go out of state to buy a car. If I'm gonna go out of state, I might as well extend my search to like all of the US and just buy a car long distance. That way I have more options. But yeah, gas prices are also crazy, so it doesn't make sense to drive even if you got a car, unless you have to. And then you might say, well, okay, should I bike everywhere for commuting? And you can, but it's extremely cold right now, so we're all in a terrible situation. You biked everywhere when it was cold. Yeah. I guess it'd be easier if you had like an e-bike, right? Because then you wouldn't have to put so much effort into it. You can find some pedal assists for decent prices. Yeah. Like e-bikes have pedal assist. A sports bike. What's a sports bike? Is it the ones with the drop bars? Oh yeah. I remember seeing those. Those look cool. All right, let's go over this question. So the number of customers arriving at a branch of a capital One cafe can be modeled with a Poisson process with lambda equals 3 customers per hour. Okay, find a probability that no customers arrive between 10:30 and 11. So the first thing we have to ask ourselves is, are we going to use the Poisson random variable or the exponential random variable? And the way we decide is to ask ourselves, are we dealing with inter-arrival times or number of customers? Because that will dictate which random variable to use. So what do you guys think?
Oh, there should be a Poisson process.
Um,
And you would,
well, yeah. I mean,
you would use the Poisson distribution here.
yeah. So regardless of what distribution we use, I mean, they're both considered Poisson processes anyways. It's just that, when you're given a Poisson process, you will use either Poisson or exponential, depending on what you're interested in the problem. So yeah, even though this is a Poisson process, it is possible that we're going to use exponential if they want inter-arrival times. So, but yeah, part A should be Poisson because this should be number of customers, no customers. So part A, probability that x equals 0, if we were to say x is the number of customers. What is our lambda? So the one they gave us is 3 customers per hour. This is only half an hour, so it'll be 1.5. 1.5 to the 0 power e to negative 1.5 over 0 factorial. Okay. Part B. Calculate the probability that the first customer arrives within 15 minutes of the cafe opening. So is this Poisson or exponential? First customer arrives within 15 minutes. So hopefully you guys can see that that's exponential. This is inter-arrival times. So we're finding the probability that x of 1, let's say x of 1 is the first inter-arrival time, is less than 15 minutes. If we want to write it in terms of hours, that's 0.25. So this is going to be, for this one, our lambda is actually going to be 3 because we're writing t in terms of hours. So we have to use the per hour lambda. So this is going to be 3 here. What was it? 1 minus e to the negative lambda times 0.25. Okay. All right. So were you guys able to get 1 and 2? I mean, A and B.
Yeah.
Okay. Part C. What is the expected inter-arrival time between each customer? So how do we do that one?
Just
Well,
be
the
one
int-
over. Sorry.
Yeah, go ahead.
I was gonna say it should just be 1 over lambda.
Yeah. So the inter-arrival time is exponential with lambda equals 3. And we know the expected value of exponential is 1 over lambda, which is 1/3 here. Okay. So yeah, your 1 over 3 is correct. But hopefully this 1 over 3 number also makes intuitive sense. So, if we're given information that customers arrive at intensity of 3 customers per hour. So if you were to imagine the time passing, right? And every hour, 3 customers arrive. So how many customers, or how should I phrase it? So 3 customers arrive every hour. How long would it take for each customer to arrive? And we expect it to be 1/3 of an hour. So hopefully that makes intuitive sense, because if one customer takes 1/3 of an hour, then in 1 hour you'll have 3 customers. So yeah. All right, that should be it. So this is Poisson processes, which involves Poisson and exponential random variables. Any general questions on this? All right. If there's no questions, then let's stop here. So on Thursday, we will continue with the very, very, very last topic of the semester, which is Markov chains. So yeah, we'll stop here for today, and we'll continue on Thursday. So have a good night, everyone, and I'll see you next time.